And my camera was off. I'm sorry. My camera had the blocker on it. How are you guys doing? Good? Okay. Please let me know next time when you see something is not working right, okay? Anyway, today we're continuation of chapter 29. And like I said, I'm working on the lab. Actually, I can show you where I stand on it right now. I think I have 95% of it done. I'm still working on the details for the simulation. Once we have that, and it should be ready this afternoon, hopefully before the actual lab when it starts. I'm sorry, also the instructions are not ready in the format, but they're ready actually in terms of instructions, what we need to do. So once those two are ready, which I'm going to post on Canvas, hopefully before or around the time of the lab, you should be able to get to do your lab. The lab today is on how to measure basically E over M. Again, this is a simulation. This is not an actual lab. This is a lot of fun if we were to do it in class, because we will have an apparatus basically where we send a beam of electrons, and those beams of electrons will be deflected in a magnetic field. And based on because they will be basically spiraling, based on the extent with which they spiral, we should be able to determine the ratio of the charge, the electronic charge, and also that of the mass of the electron. And this constant is a very important constant because it tells us about what kind of material we're dealing with. So if we know, for example, the mass of the particle, if we know the charge of the particle, if we know also the spin of the particle, if we know the electron, so of course, if we know, since we know the ratio now of E over M, and we can determine the mass, for example, or determine the charge, which is really easier to do the charge, then we can determine the mass. So we know specifically what kind of the particle that we're dealing with. So unfortunately, we're not doing it in live. We're not doing it face to face. So we're going to do a simulation where you'll be given data, and you're going to be able to measure that E over M. So that's basically what the lab today is. In terms of the lecture, again, we're continuing with chapter 29, which is part of the exam. As I promised last time, we're going to basically hold on, let me share with you a screen where we are right now first. So we're going to do an example from this chapter, as I promised, as we now have been doing in the past few chapters, where we actually pick up a problem from the chapter. I know we have an exam next week around this time, actually, and that exam is going to cover chapters 27, 28, and 29. And the review for that now is all on in terms of the homework, and also this additional 3 problems. Now, some questions came about for the mastering physics. I'm not too thrilled about the mastering physics at this point, because a lot of these problems basically they're single question problems, and they are not to the level of what this course is. So I'm thinking to stop with using it right now, keep what we did so far in it, and that would be enough. And then next semester, when I'm teaching this class, I'm not going to be actually doing things from mastering physics and rely only on the problems from the book. So that answers that question that a couple of you have been asking, actually. So if you guys don't have any question for right now, so let me first of all see what we did in this chapter. So we talked about the fact that if the magnetic field changes, okay, and this is basically, we talked, oh yeah, we covered it all the last time. We had to finish chapter 28 also. So anyway, and so we said that if the magnetic field changes in a region, what we're caring for is not the actual magnetic field. What we care for is the flux of the magnetic field, okay? Experimentally, Faraday and others have shown that there is an EMF that is established in the circuit. So today we'll try to understand the essence of that EMF, that electromotive force. Where is it coming from? And then we're going to talk a lot about the sign thing in here, because it's very important. Lenz's contribution to this law is very important in terms of the direction with which the EMF is pointing. And how changing. Okay, so we're going to continue. And then we're going to talk about the eddies. The eddies, I already did a video. I posted on YouTube, actually. I'm going to give you a link. I have an apparatus for that, so I'm going to show you what the apparatus is. and how the eddies basically work. Once we have that, then we're going to summarize everything we've learned, okay? The equations of electricity and magnetism so far. In other words, we're going to take stock of what we did so far, which is a lot. So we're going to take ownership of these things. And we're going to talk probably a little bit about superconductors, and that's probably not going to be in the test. Again, this is not a testable item. It's just for basically exploring more different materials. So in terms of tests, this is probably not as important as the other stuff before it. Okay. So let's get into basically a situation that should help us understand basically how this changing flux induces induces a current, induces an electromotive force, and we will have to really specify now what we talk about when we talk about an electromotive force. We have a problem 59 from the book. Again, as I promised, we're going to do problems from toward the end of the chapter. I don't think this problem was assigned so as a homework problem, so this is going to be also explored in class 2. So what we have in here is, let me give you an example scenario, okay? I have a magnetic field pointing into the screen, okay? So when I draw the X in here, I mean specifically that there is a magnetic field. So this is the direction of the magnetic field B. Furthermore, I'm going to assume that B is constant, okay? Uniform. So there is a region in space where there is a magnet. Think about it, that there is a North Pole in here, and on the other side of the screen, there is a South Pole. There is a magnetic field in here, okay? Okay, so if it's an electromagnet, so it's pointing this way. If it's a bar magnet, you have a north on one side and the south on the other side if it's a horseshoe, okay? So this is basically what the magnetic field region is. So this is what I'm going to do. I'm going to take a wire, okay? A wire, a simple wire. I can get my mouse to give me a different coloring thing. So here is a wire. Just for illustration purposes, I'm going to put a light bulb in here. Okay, so this is a light bulb. And to emphasize on the fact that there is no battery. In other words, if this wire is sitting by itself still and it connected to a light bulb, it doesn't matter. Nothing happens. At this point, there is no current flowing through this circuit. I'm going to assume that this wire is rigid, okay? Just for the sake of argument in here, because I don't want this wire to stretch or anything like that, so it's not going to stretch, at least with small forces. So this is rigid enough so that it doesn't stretch with small forces. This is what I'm going to do. I'm going to take this wire and move it in this direction with a velocity v, okay? Into the region of the magnetic field. What happens is, once the wire enters into the region, once it's partially immersed, not fully immersed, okay? When it's partially immersed, this is how it's going to look like. So I'm going to take another pen in here and draw it with the blue. So this is the same wire, okay? It has moved now so that part of it now is inside and the other part is outside. Now the light bulb is somewhere in here, okay? So it's still moving, it's not stopped. It's not like I pull it in and then stop. So this is still moving. What happened in this case, we will notice that the light bulb will light, okay? Although we don't have a battery. As long as it's partially immersed and it's still moving. So how can we explain that, trying to see it in terms of what's going on, in terms of what we have known so far, okay? The wire, which is a conducting wire, by the way, conductor, otherwise there is no current flowing, period, end of the story, no matter if you have a battery or no battery. If you have an insulator, there is nothing in here. So if we have a wire in here, and it's moving in this direction, so the V is pointing in this direction, the magnetic field is going into the screen, as you can clearly see. So this is V, this is B, a single charge, 1 Coulomb charge, okay, 1 Coulomb, a unit charge. Of 1 Coulomb will be subject to this force. How is this force given? Again, the right-hand rule. V is pointing this way. This is a 1 Coulomb charge. This B is into the screen. So the force now is pointing upward. So the force from this rule, using the right-hand rule, should be pointing this way. So every 1 Coulomb charge will be subject to this force. So this is again F is equal to Q. Remember, Q is 1 times V cross B. So in other words, this is a force that is exerted on a single unit charge. Okay. Obviously, the charges that are in this region, you need the B for this to happen. Otherwise, this thing is 0. You need the B. So the charges that are in here, they feel this force. I just assume that this wire is rigid, so it's not going to bend, because this force wants to bend the wire this way. Okay. The charges that are moving this way with the wire are going to be subject to this force trying to pull them up. And again, I assume that the wire is rigid enough so that this force is not going, because all this force is trying to do is bend the wire. Same thing, the charges that are moving this way also with the wire, they're going to, because they're inside the magnetic field region now, they're going to also be subject to the same force. Okay. Now, these two forces, they're trying to bend the wire, so we don't care for them, because I just assume that my wire is rigid enough that this force is not going to bend it. But the charges that are sitting in here, they're too moving in this direction with the wire. Okay. And now they're subject to this force pointing along the wire. So charges will leave this region, and because this is a conductor, they will be replaced immediately by other charges, because again, a conductor has free charges that they can move at will. So the minute the charge is depleted from here, the one next to it will replace it. So the charges, they will move in here up to this point in here. Since there is a depletion of the charges coming from here, where is it going to come? It's going to come from this side. In other words, charges will move from here, and they will end up flowing through this side and come. That's why you see the light now, because there are charges moving. So you really have a current in the wire. So that's why the light comes on. Okay. And then again, they will end up and close the circuit. So now I really have a battery without really having a battery. I have an EMF, an electromotive force. I have like just by the fact that the wire is moving, it's all due to this magnetostatic force. Okay. In this portion of the wire. The trouble with this situation is, if I continue pushing this wire, and of course we're going to get into the math part of it, but I'm trying to understand it now, at least this situation by itself. So if the wire submerges completely into this thing in here, into the magnetic field region, what happened in this case, there are wire currents that are trying to arise from here, charges that want to arise from here because of this magnetostatic force, and charges that are going to move from here too in the same direction. Now, assuming that there is symmetry, in this case, there will be enough charges trying to go up, and there is enough charges to compensate for them, and there will be cancellations. In this case, there will be no current. The light will go off in here. So no light in here. When it's completely submerged. Okay, no light when it's submerged. And when it's partially is when you will see light. When it's out, of course, there is no magnetic field. B is 0 to begin with. But the only reason why it's completely 0 when it's completely submerged into the region where there is a magnetic field is because the two sides of the wire will exert the same force on each other, but in opposite directions. So there is a no net force in this case to force the charges to move one way or the other. So that is basically how this is explained. So what I have in this situation, I have this force, okay, that is moving 1 coulomb. If I am interested trying to find the work done on the work done on a 1 coulomb charge, okay, that work is going to be this force, which is on a 1 coulomb charge, okay, times the displacement. Okay, so I'm going to assume that I'm going through the wire, because that 1 coulomb needs to run through the entire wire, by the way. So the 1 coulomb, in order to find this work, I need to take 1 coulomb from here. It doesn't matter where I start, by the way. I take it from anywhere in the wire, and it needs to move back to close the circuit. So the work done on a 1 coulomb charge is going to be, by definition, the electromotive force, which is usually represented by EMF. So when you hear me and you read the book and it says, what is the EMF? All they are asking for is the work needed to move 1 coulomb charge. Again, to go back to the example of a normal battery, that is actually the EMF too. That is a 9-volt battery. That is the EMF. That is the work needed to move 1 coulomb charge from one side to the other side of the battery. Okay, that is what the EMF is, and it's measured in volts. Okay. Now, if you don't have 1 coulomb, if you're not running really 1 coulomb, but running a different charge, 5 coulomb, 10 coulombs, 0.2 coulombs, or 1 microcoulomb, then you multiply the number of charge times that voltage, and that is the work actually in joules, and the actual work in joules. So again, if you guys remember when we were doing electrostatics, we found the work or the energy is Q times V. That is the formula that we go by. But at this point, the V itself with no Q, or Q is 1, is in this situation what we mean by, I mean, it's voltage, yes, but in this situation, it's specific voltage because there is a battery now. Although this battery, I don't see it, it's due to the fact that this wire is changing in this magnetic field region. So let's try to find this work in here. So the EMF now is going to be the integral over the entire loop of the entire wire, closed wire, of this force, which is going to be F times the displacement. And the displacement is along the wire itself. Okay? So this is basically in a nutshell what this thing is. So this is how we calculate. And remember that this force is a force on a unit charge. Okay? So this is a force, not the entire force, by the way, force on 1 coulomb charge. In other words, unit charge. Okay. So the answer obviously is going to be in volts. So this is going to be in volts. So again, it's V crossed with B times the displacement in this case. And the displacement, sometimes you find that you use DL. So probably we should use DL, but it doesn't matter. So this is the displacement along the wire itself. Okay, so this is the EMF. Now, you're trying to find this expression in here in terms of this force, okay? Here is another way of looking at this expression. If I am interested into this area only, I'm going to take now a more mathematical approach to this wire in here. I'm going to say the width of this wire is a W width, and the length of it is L. And as the wire is moving, it's moving in the X direction, so that this is actually the only portion that is merged in this case is X, or I can label it differently. So the rate with which X is increasing is exactly V. So in other words, V is simply dx over dt. Okay. So as long as I have that understanding, then I'm in business, okay? But note this force in here and the displacement in the wire, they're parallel to one another. So at the end, this product of this force and the dr is going, because don't get confused between the V times dr. Of course, they are perpendicular in that region, but I'm looking at V cross dr, which is really parallel to it, okay? Here is, first of all, before I go any further, and we're going to talk about the area very closely because that is actually the rate at which this area is changing with time, okay? Because part of B is dx times dr, and the dx is this element in here, and the dr is this element in here. So this is actually the element of the area itself, okay, as it's changing. So this is dA. So this is dA because the dr and part of the V, which is the dx, times one another, that is the area itself. And of course, the whole thing is divided by dt. So I can argue in here and say that actually this is B times dA, okay? So this expression itself is actually B times dA, but I'm taking the dt completely outside. So right now I'm integrating over an area. I'm not integrating over an element, because I'm looking into this dx times dy, if you wish, because the y is in this direction. So this is the area itself that we're integrating, and we're integrating through the entire area in here, as long as we have a magnetic field that is changing in that area. So the point being in here is, this is B times dA over the area itself where the magnetic field is changing. Okay? This whole thing, of course, is the change in the area with respect to time. Okay? So this is why we can argue and say that this is the EMF with which it's pointing. Okay? At least the value of the EMF. I'm not talking about the direction of the current. Okay? So the EMF at the end, we can argue from this point in here that this is the rate. So I'm looking at it in absolute value. I don't care at this point about the rate at which the flux is changing with time. Let's look at another issue in here, which does this make sense, first of all, in terms of a force? Yes or no? As the wire is moving in this direction, the charges in this wire itself, they're moving upward. Because I'm going to open another question, which is really part of the question of the day. Okay? And we need to answer it. We argued a long time ago that any charge, I'm not talking about a specific charge, no, any charge Q, inside a magnetic field is going to be subject to this force. Okay, this is part of the Lorentz force that we discussed a long time ago. Okay, because of that, we said that this force does not do work, because if I'm trying to find the power is just force times velocity. And the force in this case is perpendicular to the velocity because it's coming from this cross product. Now, when I dot it with the velocity itself, this is perpendicular to V, because V cross B has to be perpendicular to both V and B. So in particular, it's perpendicular to V itself, to the velocity. When I dot it with V, it's going to involve a cosine of 90 degrees. And a cosine of 90 degrees is 0, so there is no power. Magnetic field does not have power, does not generate, there is no power associated with it. And power, remember, is the rate at which work is done. So if there is no power, there is no work. So the magnetic field does not do work. B does not do work. Here is the trouble. So why in the world then we have the light going on? If there is no work, if the magnetic field does not do work, so why are we getting some power in here? How is the light bulb going on? So who is doing work now? That's the question. First of all, before I have you guys understand, do you guys understand the situation first or not? Do you understand how this problem works? I mean, I have a bunch of wires in here, of course. Let's take this wire. Of course, this wire is too thick. Okay, it's not going to work. We discussed this is a gauge 20 wire. It's going to work, but it's going to have tremendously weak magnetic, weak current that we're not going to see it. Even with the multimeter, we're not going to detect it, let alone light bulb. Take this wire, connect a light bulb to it. You have to close it. You have to connect the wires at the end. Okay, you have to close the circuit. If you leave them open, and this is part of problem 59 actually, what you will end up with is an EMF that builds up. There will be pile up of charges on one side and depletion of charges from the other side. So in other words, you will see an EMF. The minute you connect them with, for example, a light bulb or a resistor or whatever, so I mean any device in here, there will be current flowing because of that EMF. So if you take this wire and you run it across magnets, I have a bunch of magnets in here, okay? There should be a current as long as it's moving, okay? As long as either the magnetic field is moving, in this situation, in this example, the magnetic field is not moving, or actually the wire itself is moving, like in this situation, the picture I drew in here, okay? So there will be an EMF, which is basically a work done on a single coulomb, Now you're telling me, oh, there is no coulomb in here that run. It's a fraction of a coulomb. That's fine. Then multiply that fraction and you find it actually in joules. But what you will do and find it if it's a unit charge is going to be in volts. Okay. So that is a work done per unit charge. So there is an EMF in this. Do you guys understand this picture or not? I want to really see that there is a consensus on it, that you guys are okay with it. First of all, there is no battery in the circuit, and I have a wire. And to illustrate the point that there is a charge in it, I just put a light bulb in there. Of course, if the current is too weak, I may just put, for example, an ammeter in there, or a diode, for example. Okay, if there is a strong enough voltage, usually about 5 volts or something like that, to turn on the diode, you will see light. You will see something that's going to come off by itself. Okay, of course, this is, if we're in the lab, we can do it actually, and we will see how that works in terms of that. But I'm hoping that you guys have a physical argument based on the math that I just did, with the fact that a single unit charge will be subject to the force V cross B, since I chose V to be pointing in this direction. Okay, when I move the wire this way, that's the velocity of the wire. And I chose there is a magnetic field pointing into the picture. Then it's crossed clearly. There is a V, there is a force that is going to be pointing upward, okay, on the wire. And that force then, because in the other sides of the wire that are also moving in the magnetic field, all it's trying to do is basically push it upward or trying to deform it. And I'm going to assume in this situation that the wire is rigid enough, so it's only it's not going to bend one way or the other. So, but the charges now can move through the wire. So in the portion that is vertical, they can move through the wire, and then they close the circuit because this is a conductor. It's not going to allow pile up of charges anywhere, or depletion of charges on the other side. So it's going to replace them immediately or move these ones at will. The minute they move, then you have a current in this situation, okay? Without a battery, without actually having an external battery or a power source other than this one. Do you guys understand this situation or not? Yes or no? Okay, Daniel at least agrees. Anybody else? Okay, Alex too. So Sebastian and everybody. So this is basically how this works. So that is exactly the situation I described it. So in other words, for example, if the power goes out tomorrow in your household, all you have to do is call your neighbors and have them run a magnet underneath, and you can watch your favorite show or your favorite TV thing, because then the power will be reestablished. Okay, as long as they're moving the magnet. Okay, make sure they don't stop. If they stop, then you run out of wire. Okay, you can hire some of your classmates. Does this sound like it's a good plan to help one another? No? Nobody else is taking it? Okay. Why not? Okay. So anyway, the point being in here, that is a way of generating as electricity. As a matter of fact, that is how we get power to our households. I mean, it's not having our neighbors run it to run a magnet, but that's actually how the power is generated in the Hoover Dam or whatever that we get our power from. Even if it's not a even if it's not a whatchamacallit, even if it's, because in the Hoover Dam or the water that is actually moving the wires and making them turn around big magnets, and that in turn will give you a current. Okay, will give you EMF that is delivered all the way to here. Okay, and other places where they don't use water, they use actually power generators, for example, using gasoline or using other kinds of fuel. It doesn't matter, it's still the same process. We're going to talk about power generation and how it's made actually to get into the AC current. Okay, but that is the process through which power is generated using for the alternating current. So that is basically the idea behind it, except in this situation, what I described is that we have a wire moving. Obviously, if the other situation also is true. So in other words, if I have a magnet, let me go back into the picture where we were. What is it? Share. So in other words, if I go back to this picture and hold the wire still, but carry now the magnet and move it in the opposite direction, it's the same thing. Okay, these charges now, they will be subject to this basically as if they're subject to that. So if you use the relativity in this case, even classical relativity, they can you can argue then that in this situation that the force will be the same and the EMF will be established. Okay, the mathematical argument is a little bit cumbersome, and I really don't feel like doing, especially in this online environment, because it really involves a lot of basically drawings and things like that. But the point being in here is, if the wire moves through the magnet, or the magnet moves through the wire, or both, you will end up with the light going on. Okay. My question is this, based on this argument that we did last time. Okay. Whether it's a single unit charge or a million coulombs, it doesn't matter. The magnetic field does not do no work, period, end of the story, bottom line. So my question is, how come we're getting power generated in here? How come we have work in here? How come this light bulb in here is going on? What do you guys think? Who's doing work in this situation? If the magnetic field does not. Okay, let me give you the choices, okay? How many choices do you think you have? Can anybody tell me? Roughly? Any number? I'm going to give you choices to choose between. Choice 1, 2, 3, 4, 5. And at some point, I think I need to stop from giving you more choices because I will run out of choices. So my question for you guys, how many choices do you think you will have? Roughly. I need the number. 3 choices, Alex thinks. At least Alex was courageous enough to suggest a number. Anybody else? More or less? Daniel thinks 2. Anybody else? Come on, guys. Heather thinks it's 2. Okay, either Daniel or Heather, I need to know what 2 you think they might be. Because there are 2, actually. 2 choices. You're only going to be given 2 choices. One of them is the one that I said doesn't do work, of course. That is a choice, but I already answered that. That's not going to be an option. In other words, that is actually one of the 2 choices. The magnetic field is choice 1. Okay, but that's not it. So if it's not the magnetic field, what other choice is? Now the velocity is not. I mean, there should be a field, first of all. Okay. I mean, I can take this wire and move it, of course, inside, but the velocity in this case should not be an option. There are 2 fields in here. One of them, I said, does not do work. End of the story, period. Go home. I mean, forget about him. Okay. There is another field that could do it. What other field we learn in this class? Electric field. That is the only guy left in town. You guys understand? You only have 2 options, really. Option 1, the magnetic field, and I just argued the magnetic field does not do work, period, end of the story, go home. Okay? Forget about it. Then the only choice left, actually, is the electric field. But Alex, I know you suggested it, but now why where is the electric field? There is no battery in here. Let me go back to the point in here where we are. I mean, you're right. It is the electric field, but how can we argue? Where is it? Let me go back to the picture again. Oh man, every time I leave this thing, it freezes. So let me go back into this. We only have a magnetic field region. We decided to move the wire into it. Okay. and we notice the light going on. So what Alex is suggesting, since we only have two fields that we learned in this class, the electric field and the magnetic field. The magnetic field is not an option. The magnetic field does not do no work, period. And because of this relationship, it's perpendicular always to V. And when I dot it with V to find the power, I will end up with 0. Okay? So there is no power, there is no work. Okay? The magnetic field is not an option. So the only option left for you is to say that there is an electric field in this region in here space. Okay? And this electric field must be the electric field must be induced by the changing flux, because what happened in here, you have the flux, which B times dA, by the way. This is the flux of the magnetic field, okay, in this region of space, changing magnetic flux with time. The reason why I have to think of the flux is because B is constant. I cannot say B is changing. But B times dA, B times this area, because the wire is moving, it has to be the flux then. B times the area. Because in this region also, the flux, the wire is moving and there is no magnetic field. So I cannot say that there is a flux in this region. So the flux exists only in this region where there is an inward of charges. So that's why I have to say that it's actually, this electric field must be induced to that. But even if I argue that, and I'm going to show that it is the case, who is actually doing the work now? That still, we did not really answer the question. Yes, the electric field, because the electric field, let me argue why that is, because the electric field will do actually work. The electric field, if there is one, okay, the force due to the electric field is Q times E for any charge. So I can argue that there is power now, which is F times V. As long as E and V are not perpendicular, this number is not 0. Okay? So this is actually equal to Q times E dot V. Okay? And this is fine. Okay? So this does not have to be 0. As a matter of fact, this must be the quantity that is giving me the light to go on. Okay? But at the end of the day, this electric field is actually created by the magnetic field as it changes, as its flux changes. But my question is, who is actually doing the actual work altogether? The bottom line. So the two choices, one of them is not possible. The second one, yes, is doing work, but the second one is really a problem because it's created by the one that doesn't do work, okay? But at the end of the day, somebody is actually doing the work. Can you guess who that person is? Any idea? While you're thinking about it, let me grab my Eddie's apparatus and I'll be back, okay? It's just basically a demonstrator. Hold on. How are you guys doing? Did you find some answer to that? Here is basically a copper wire. I'm in a tube, okay? So this is basically, you can clearly see from here that this is hollow. Where is the camera? Okay. This is hollow. I have two metals in here. This is one, and this is the other. This one, I have in here a piece of iron. This one is not magnetic, as you can clearly see. This one is magnetic, okay? And they are both identical in shape, okay? They are both identical in shape. Now they're attracted because there is another magnet, because this one actually is a metal too. So if I remove that magnet, this is not going to be attracted to anything. I'm going to put it on top so that it rests, but the minute I turn it, okay, it's going to fall because this is not magnetic. When I let them go through this hole in here, one of them, actually I have the link for you guys. Let me give you the link in here too, okay? It's actually on my YouTube account because I posted it, part of the demo, because it's not going to work in here because you have to be looking through the opening to see exactly the okay, so let me get the oh, can I play this while you guys are here? Yeah, probably I should do that. Hold on. Okay, so let me share with you that screen. Hold on. Can I put it on no, I can't do that now since I want to share that screen. Share. Do you guys see the player now? Yes or no? Because I'm in full screen mode. I cannot see nothing in here. Confirmation, please. Yes. I cannot see the chat, okay? Somebody has to remove the microphone and tell me yes or no.
Yes.
Okay, so this is basically the demonstration. Okay. So this is now the metal. Immediately goes through because of the gravity. Now this is a magnet. Look at it, it's going to go slow down. Okay, here is again iron, no magnet. Immediately goes through, falls through due to gravity. This is now with a magnet. This is not slowed down or anything like that. This is a weak magnet. The last one in here is a super weak magnet, but it's also almost falls through. Okay, so let me cancel. I don't know what is that. Stop sharing. Will you stop sharing in here? So anyway, that's part of the eddies, which we're going to explain it, but I still need the answer to that. Who is actually doing the work at the end of the day in this situation? And it's not the magnetic field, and it's not the velocity, and it's not the wire either, because the wire by itself should not do work. In a sense, it's kind of a velocity, but it is not the velocity directly. When you run out of electricity, what did I say that you should do to your neighbors? What should they do? Should go and call them and have them come and do what? To get you to watch your favorite show or play your game on Xbox or something. You give them a big magnet, and what are they going to do with it? Come on, guys, you should remember this. We just talked about it. Okay, so they have to move that magnet around your house, basically. That's correct, okay? So who's actually doing the work now? Is it you playing that game or watching your TV, or is it? Who is doing all the work? Yes, the people who are moving the magnet, actually they will feel resistance because of the same thing I was talking about in here. The wire is going to be heavy to move through a magnet. It's not going to be easy. They really have to exert the force. And how much force they need to exert? They need to exert exactly V cross B per charge, per unit charge. in order for them to successfully generate that power for you so that you watch your favorite TV or something like that. So in other words, those neighbors, they need to be paid. Actually, you need to give them something in their, if you're not paying the power company to deliver that power to you, and you decided on bringing your neighbors and have them help you out, then you really probably need to pay them, because they have to force V cross B, and they're actually the ones who are doing the work. So whoever is moving this wire in this example is the one who's doing actually the work. So what is the role of the magnetic field in here? Although it does not do work directly, it helps work to be done. It helps you decide which charges they move. It does not move them on its own. It does not do nothing in terms of work, but it gets work to be done. It's like your boss, basically. The boss is usually sitting and doing nothing. But without him or her, you cannot get work done, because everybody will go home and do nothing, okay? So that is, in a sense, the equivalence of what is going on in here in terms of this circuit. If you remove the magnet, if you wish, there will be no charge. You still are out of luck, because you cannot have the light bulb going on. So in other words, the presence of the magnetic field, because if you don't have a magnetic field, what you could do for this wire is actually you go individually to inside the wire, like this copper, for example, and move the electrons, electron by electron, from one side to the other, okay? Obviously, this is not feasible, okay? Imagine yourself going through this wire and trying to find the charges from one end and move them through this entire wire and put them through the other side. Now, the magnetic field does not do work, but helps you do this. So that is, in actuality, the person who is moving the wire is the one who's doing work, and the magnetic field is helping that work to be done without actually doing the work in here. It takes it from your hand and deliver it to somebody else, which is the electric field that it induces, and the electric field now does the work. Because there was no electric field to begin with to be in the circuit. So this electric field is basically created by the magnetic field, okay, to do that. As a matter of fact, this is what I'm going to do to this expression. I'm going to assume that there is, because that's the only guy, that's the only force that we know in this context that does work. So I'm going to assume that then there is an electric field that is induced per this relationship, per unit charge also, so that this is true, whereas in this case, the work done on it is given by that expression. So the EMF in this situation is the E induced, okay, throughout the entire circuit times the element of the circuit, okay? So this is basically what we mean by the EMF in this case. This is fine. Now we're good. We're fine. So this E induced is related, if you wish, to this V cross B, okay? To this, okay? The trouble with this expression, please don't think about it that it is equal to 0 in this situation, because V now is in this direction, and you might think, okay, V is perpendicular to the R, therefore it's going. No, what I'm looking for is the product V cross B, which end up in this direction. Okay. As a matter of fact, there are two velocities in here. If we really are careful with this problem, we have for every charge, the charge is moving with the wire in this direction, but it's also moving through the wire in here. So it has a perpendicular direction in here, which the sum of these two velocities. Okay. So that is in actuality where we need to put this expression, and we can show that the work is exchanged that way. So I hope that this illustrates the point that the EMF in this situation is due to this expression. Now, and this EMF again is given by that. We have only one issue here, and that is the direction. The direction. Okay. The way I have my current right now is clearly the EMF is counterclockwise. It's positive. It's going this way. The charges are moving in the positive direction. Okay. However, as the wire is moving this way, more and more field lines will go inward, will go into the picture, because as the wire moves this way, more field lines are going this way. But the EMF has a current basically going counterclockwise, as if Now, if this EMF can create its magnetic field, then it does in this situation, it's going to create a magnetic field given by the right-hand rule. The current is curling counterclockwise, so the magnetic field created by this current is coming out of the picture. So this magnetic field is not the one that is, this is the applied magnetic field, okay, B, that is inward. This is not the applied, this is the one that is being created by this EMF. As this EMF is counterclockwise and there is a current now, this is the current I, okay, flowing in this direction. Since the current is going counterclockwise, then the EMF, the magnetic field it creates, because again, Ampere's law still holds in this case, since they have a current now, is going to create its magnetic field, but the magnetic field now will be in the opposite direction. So the more field lines are going in, this EMF will create will be in such a way that it's going to compensate for the ever increasing field lines inward. So it's going to make them outward. So the sign in here is the problem. Because I'm going to keep it in red, okay? I'm not going to change the color because this is very important. Okay, because the field lines, the B field lines, okay, this is the applied, are increasing towards the inside of the screen. I just showed that the charges will move counterclockwise because that's where the force is pointing. That will move counterclockwise. So in this case, if it's moving counterclockwise, the magnetic field that they create is going to be coming out of the screen. Okay? Because of the B field lines are increasing towards the inside of the screen, the induced EMF generates a current, that is a current that is generated, it's counterclockwise, that current itself now it's running, so it's running per Ampere law is going to create its magnetic field. So that generates a magnetic field with field lines coming out of the screen. Okay, to compensate, sorry, it's not complete yet, the statement. To compensate for the ever increasing field lines, applied field lines, to make sure that we're good, applied field lines into the screen. So that's basically the whole idea. So we are going to put a big statement now for Faraday's law. In Faraday's law, this is true all the time, we'll have two components of it. First of all, the magnitude, which is easy, and then the direction that has to do with what I just said, okay? So in general, okay, a changing magnetic flux okay, will generate an EMF. Now, an EMF may or may not create a current, okay? If the loop is open, it's not just, there is no current, okay? It's just a pile up of charges from one end and depletion of charges from the other end. So it's like this battery now. When you have an EMF, you can have it just like this one, okay? So that is exactly what it is. If you connect the wires, now you have a current, Okay, so will generate an EMF so that, first of all, given by, because that we need the by the rate of change of the flux, of the magnetic flux. Okay, with time. The rate is meaning with time. Okay. The direction is the issue. Okay, the direction is really the issue. So basically, the EMF mathematically in absolute value is equal to d phi of b with respect to time, and in phi of b is just the integral over the surface. This is not closed. Okay, if it's closed, it's zero. We know that. So it's b dA. So that is the mathematical expression for the rate, the EMF, but that's in absolute value. The direction now is the issue. The direction of this EMF, electromotive force, is so that if it creates a current or generates a current, this current, so it's not always true that it can generate a current. That's why there is an if in here, okay? If the circuit is closed, then it's going to generate current. This current will create a magnetic field per Ampere's law. Remember, Ampere's law says that the circulation of the magnetic field over a closed loop is equal to mu naught times I. Since I already have I, now I have a magnetic field. So there is no need, it's not necessarily true that it's going. So if you're trying to find the direction and it's not closed, assume it's closed and find the direction and then go back to the fact that it's not closed circuit, okay? So that to find at least the direction of the EMF, which side is positive and which side is negative, okay? So that the magnetic field will create a magnetic field. What is it? This current will create a magnetic field so that it compensates for the changing flux of the applied one. It's a mouthful. It really is, okay? And it's really, sometimes there is so many words in it that it's probably convoluted and it may be confusing a little bit, especially since we are not in class and we talk about it. But the only way to really understand this one is by applying it, okay? That's the only thing I can tell you. So if you take a circuit, you have to pay attention, where is the magnetic field changing in order to find the direction? Once you find it, then you know, because it's going to make a big difference for your result, the direction. You could end up, for example, with 7 amps, or you can end up with 2 amps for the whole problem, or the resistor or something like that, and you end up with something completely different. Mathematically, this part actually is due to Lenz, okay, of the law. The first one is to Mr. Faraday. Mathematically, you just put a symbol in here, minus d phi over b over dt, okay? So this is what this whole thing means, okay? So if the field lines are increasing, then you have a problem. If the field lines are decreasing, then you have a problem. Let's take an example, okay? Here I have a wire, okay, closed loop, and I have a bar magnet in here. This is the north, and this is the south. If the magnet is moving this way, I want to know which way the current is moving. I don't care about the magnitude, okay? So here is the field lines. So these are the field lines of the magnetic field, okay? As this wire is moving in this direction, more and more field lines are going this way. You guys see that? More and more field lines are moving into the picture this way, okay? So the current that is going to be generated in the wire is so that is going to have its magnetic field pointing in the opposite direction. So the B induced in this case is going to be pointing this way, because next time this wire moves a second, two lines, for example, come in. If two lines come in, this will create its two lines. Say if every second there are two lines coming, it's going to create two lines every time to compensate for the ever increasing field lines this way. So it's going to create its magnetic field this way. So now I know the direction of the magnetic field is pointing this way. So the current must be curling counterclockwise in this situation. So the current is this way. And that is how I know the direction of the magnetic field. If the magnetic field is moving this way. Same thing. If the wire is actually moving and the magnet is still stationary, then in this case, but it's moving toward the magnet, then it's going to be this way. Now, if the wire is moving in the opposite direction, if the magnet is moving in the opposite direction, I'm going to redraw the same picture to see how this works. I'm going to have the same wire in here. I'm going to take the magnet pointing in the same direction also. So with north this way and south this way. But now it's moving this way. The magnet is moving in this direction. So the field lines are still pointing more or this way. But as the wire is moving this way, less and less field lines are going to go through it. Because the next time probably we're going to lose this line, and some time in the future we're going to lose this too, and so on and so forth. Because as the wire is moving this way, so this one will generate a current in such a way to compensate for this decreasing field lines. There are less and less of them. So it has to generate a current in such a way it's going to compensate for the ones that are leaving. So if every second I lose two, so it's going to increase two on this side. Okay? So if the magnet is moving in the opposite direction, it's going to create a magnetic field pointing that way. That means the current now has to go clockwise. So the current now has to run in the opposite direction. Okay? Has to run in the opposite direction to compensate for that. So that is basically in a nutshell how this works. Now, if you take the magnet and flip it around, I think this is usually explained in the textbook. So I'm going to go back into the same situation. And I have my magnet now flipped. So the south pole is this way. South pole is this way, and the north pole is this way. I'm going the magnet in this direction. So now the field lines are going into the magnet because it's a south pole. Okay? As the wire is going this way, more and more of them actually are going to go this way. More and more field lines are going to go this way. So this now will generate its magnetic field to compensate for the ones that are coming this way. So it's going to generate its magnetic field this way, because the next time this one will come in, but then in this opposite direction, so it's going to increase. So it's going to make up for those by running a current in the opposite direction. So again, the current in this case is going to be actually clockwise. Okay, now here is the last situation of this. If you have a magnet, again, we're going to go with the same situation of a wire with no charge in it, with no battery, in it, and I have a south pole this way and a north pole this way. And now the wire is moving in this direction. Okay? As the wire is moving in this direction, less and less field lines now will move in this direction. So the next time the magnet moves further, I'm going to lose probably this one, and I'm going to lose this one, and the next one is going to move this two, and so on and so forth. So now the wire will compensate for this one that is losing them in this direction. So it's going to add few on the opposite direction. Every time it loses one, it's going to make up for it. And because the magnetic field now is in this direction, so the current now must be flowing counterclockwise. Do you guys understand this example? Because this is really the essence of it. It's a whole big deal. Look, even when you are in upper division classes, this is a confusing thing. So I must tell you this, okay? Even if you take, I don't know, the next upper division classes, This is a little bit confusing, and it's the sign that is usually the headache, not the actual calculation. A lot of times it's just easier to do the calculation than to actually understand which way the EMF is pointing. Because this is actually will generate a magnetic field. That if is fulfilled now. Remember in my statement I said there is if. In this situation it will create a current because of the fact that the loop is closed. Imagine that this loop is not closed. Actually it's just a wire sitting by itself at an arc. Then there is a pileup of charges from one side and a depletion of charges on the opposite side. And in this situation, then you'll have to understand it. You'll have to understand what's going on. And I did not talk about this, but I hope you guys realize that this picture in practice actually is completely reversed. Just not, hopefully not to confuse you. And I know that I said the charges are moving this way, but you and I know that these charges are negatively charged. So in other words, the actual charges are actually negative. So the electrons are actually moving in the opposite direction. And that's in a net effect to see the current moving in this direction. So the same thing is true in here. But the picture is perfect in this situation, that this is actually where the current is flowing. You and I know that the electrons are moving in the opposite direction because they have a negative sign of what's going on. Okay, do you guys understand the question of the day first and this picture, because it's critical, okay? This whole thing is the foundation of this whole argument. I want to see confirmation that these two ideas, first of all, the question into who was doing the work. The work initially was due to, it cannot be done by the magnetic field, the only field in town, and we're going to talk more about it shortly, that electric field that is created by the magnetic field, and that will turn out to be a very, very, very weird electric field. We're going to explore all of its features, okay, or weirdness if you wish. And the other question was basically this sign issue. Do you guys understand the sign issue? Do you understand those three diagrams? 4 diagrams, I should say. I want an honest truth now answer to this last question. Okay, since you guys are not answering, I want everybody to tell me now, who are here, whether or not this 4 examples, 4 pictures are clear. Because we cannot proceed. I mean, we cannot do problems well if we don't understand this last thing with the sign issue. Okay, let's go. Yes or no? Clear or not? That's the second question then. Come on, guys. Be honest about it. I need feedback, guys. Okay. Okay, at least the 3 guys who, at least the 2 guys. Okay, let me go back into it, okay? So the question, Daniel, was, the second part is, was it clear, those 3 examples, 4 examples, illustrations on how to find the direction of the EMF or the direction of the current? I gave 4 pictures for examples. Since a couple of you are already asking to go through it again, let me go through it again so that we understand it, okay? I'm going to start afresh on this, okay? Because sometimes when you don't start afresh, it gets confusing. So it's actually much better to start new on this. So here is the example. I have a wire, okay? It's sitting still. At this point, there is no problem with it. I bring a magnet with the north pointing this way and the south pointing this way. I know the field lines are going to point out of, I mean, into the South Pole, but out of the North Pole. So I have a field line going this way. I have a field line going this way. I have another one going this way. I have another one barely touching the loop. Same thing in here. I'm going to try to be as symmetrical as I can, and probably one more just for the illustration purposes, and here two more. Okay. So, assuming the wire is moving in this direction. Okay. What happened next? Of course, these lines are already in. I have 1, 2, 3, 4, 5 lines are already in. The next time, there will be 2 more lines in. Do you guys see that? Since there are increasing field lines this way, the loop itself will generate its magnetic field to compensate for these ones that have come in. So it's going to make up for them by canceling them, basically. Okay? So it's going to generate a magnetic field to cancel this increasing field lines in this direction by creating its magnetic field in the opposite direction, so that this 2 will cancel. And this 2, I'm sorry, I'm kind of compensating for this one because the others are already in. Once they are in, they are in. Now, the next time this comes in, again, this will move and so on and so forth. So in other words, if I increase a bunch of them at once, it's going to create a strong one in the opposite direction. If they create very little at once, it's going to create very little. So the strength of the EMF depends on the rate, of course, depends on the velocity. But I don't care about the strength. All I care about is direction only at this point. Since now I have a magnetic field, so this is the magnetic field induced. Not always you will have a magnetic field. If this wire is open, then of course you're not going to have a current. In other words, you're not going to have a magnetic field. But if it were to do it, like if it's closed and it can run a current, this is what happens. Okay? This is just to get the direction of the B field. So now I know the direction of the magnetic field this way. So the current, the magnetic field now, according to this picture, is counterclockwise. So that is the current that is going to generate this B. So this is the direction. It's going to be counterclockwise. Okay. Now, is this clear? This example, first example. Because the field lines, there are a bunch of them coming this way, so it has to compensate for it by making one in the opposite direction. And in doing so, it's going to basically generate a current counterclockwise because the magnetic field it's making in this direction. So in this case, it's going to come out that way. Is this clear? There are quite few people I don't hear from. I need to hear from everybody. Is this example clear or not? Okay, Daniel thinks so. At least 1 or 2 more people. Okay, very good. So let's take the second example. It's the same situation, except now we're going to move it in the opposite direction so that to find where the direction of the EMF is. Okay. So think about it. Now I have the same wire. Oh, I need to draw it in the same colors to get that more sense. So we have the same wire. It's closed wire. And I have the same magnet and the same north facing and south facing. The same field lines as before. Okay. Coming out. Okay, one more this way. But now, instead of the wire moving into instead of the magnet moving into the wire, we're going to have the magnet moving out of the wire. So next time we're going to lose this, and next time we're going to lose this probably too with it. So the field lines are decreasing in this direction. So now the EMF that is generated is going to compensate for this ones by making them in the opposite direction, because it's losing them in this way as the magnet is moving away. So less and less field lines are going to go across it. So it's going to compensate for them by having them move in the opposite direction to make up the same number. It doesn't like the changing of the flux. That's why it's doing that. Okay, it's like the mass in the case of the swing, once it comes to, it doesn't want to stop. So it's like an inertia in this case, okay? So it doesn't like this to change. So in this situation, the magnetic field will be in this direction. So the current must be going in the opposite direction now, which is clockwise. That is the one that is going to give me the magnetic field pointing in this direction. Is this example clear now? When the magnet is moving in the opposite direction, you will create a magnetic field that is clockwise now. Yes? Okay, Daniel thinks it's okay. Anybody else? Okay, Sebastian. Okay, so basically that is reverse situation. This is kind of easy, but when you flip the magnet, it's a little bit confusing, but hopefully we can understand it also too. So we're going to back in here to the same picture. We're going to go, oh man, we go back in here, come back. So what we have now, we have the same wire. We have the same magnet, except it's flipped now. South is this way and north this way. And because the magnet now is this way, so the field lines are going into it actually, not out of it, because this is the south pole. What I'm going to assume now is the bar magnet is moving into the wire. Since the bar magnet is moving into the wire, the next time it's going to come closer. This one actually will come in. This one also will come in. But it's in the opposite direction. More and more field line will actually point this way. So again, it's going to generate its magnetic field to compensate for the ones that are coming into it. So by making a magnetic field in the opposite direction, which makes it in this situation also give me, so more and more field lines pointing this way. So again, because of Ampere's law, then the magnetic field, it's going this way. So in this case, it's going to be clockwise. Okay. And the last picture, it's the same thing, except that the wire, the loop, the magnet is moving away from it. So here is the south, here is the north. The direction now is this way. The wire is this way. So now the field lines are here. There's one in here probably and another one in here. As the wire is moving away, the next time we were going to lose this. This is going to be lost, so it's going to make up for it. And this one also going to be lost, so it's going to make up for it. And the next cycle and so on and so forth. Since it's going to generate a magnetic field now to compensate for the ones that is losing, and it's pointing in this direction, so the magnetic field will actually, the current has to flow in this direction, counterclockwise. I hope that this example makes sense. If not, try to play with it and understand it, because it's critical in understanding the direction of the magnetic field, which way it points. Most of the times when you have problems in the homework or the exam, you have two things. First thing is find the EMF, the magnitude of the EMF, how many volts that is, 2.5, 4.5 volts, whatever that is, okay? And then deal with the sense of it, the direction of it, okay? And you have to deal with the direction as soon as possible because your calculation will depend on it, okay? The whole thing will rely on that direction, which way it's pointing, okay? Now, as I said before, I know we have a couple of minutes right now. Since the lab is not ready and you have the lab for this afternoon, what I'm suggesting is, because we have to take a break, I don't think that you guys can take any more, and I personally cannot talk more than an hour and, 25 minutes we've been going at this. Here is the choices. Do you guys want to finish this class today and then finish the lab later, or we finish it, I'll post the lab today, so tonight, so that you can work on it and finish the lecture on Wednesday? It's up to you guys. Doesn't make much difference for me as long as I can go and get some water. The ones who are here anyway. Any suggestions? Okay. The Alex, basically, the lab, we're going. I'm going to finish it right now in about 20 minutes, and I should post it on Canvas. And the instruction and everything should be easy enough for you guys to do it. Hopefully you do it tonight, and then on Wednesday we continue the class. That's choice one. Choice two is to continue this class at 2:30 during lab time, and the lab will be posted later after in the evening or tomorrow morning. So at least Heather, I don't know what Daniel is saying. What do you think? Okay, Sebastian. Okay, so we have a couple of people now. So, okay, so let's finish this on Wednesday, but please log in back into the lab, and I'm going to send an email back right away to tell you that it's ready. This is basically what we need to do. I know it's 2:10, and so we're supposed to end. So give me a minute or two to wrap up things so that we have an understanding of where we stand, okay? So what is the share screen? Because I need to go back into this picture. Okay, please somebody else. Okay, so let's say where we are right now. So we covered most of the stuff that needs to be covered. I even demoed the eddies, okay, and I will explain how the eddies form, and it's basically based on this law itself, okay. Then we're going to summarize everything on Wednesday, which is a big deal, and then we discover that there is a flaw, that there is something the matter with Ampere's law, and then we'll talk briefly on superconductors and do the example as I promised, okay. So this will cover all the material. And I'm relying on you that you guys do the review for the problems. If you have difficulty with one of them, please let me know. The exam is going to be on Monday because there is no class on Wednesday next week, okay? So I'm going to finish your lab. The instructions of it should be easy enough to find the E over M. All you have to do is run the simulations and put the data, and it should tell you what the error is, and you should have an understanding on how to do it. Okay? If you have difficulty with the lab, also please let me know, okay? And I will also have probably also video instructions on it. I know some instructors, they don't do live sessions, they do just videos. So we will do this on videos. Okay, so I'll see you guys on Wednesday, but please log back in the minute you see the email so that to start working on your lab, okay? Let me stop the recording now.